Hi, so what we're going to look at now is what happens when we take an alcohol and react it with HCl, HBr, HI, so essentially any halogen acid. Okay? So one of the things that we're going to think about is alcohols typically aren't good leaving groups. The way we can convert them to good leaving groups, though, is by switching them to water. Alright, so the HCl in this case is going to have two kind of roles. One is it's going to donate a proton to the OH, and what it's going to do is make it water, so the water can leave. And then the chlorine is going to take its place. Alright, so in this case, let's just draw the carbon backbone the way it is. And then in the place of wherever the alcohol was, we'll put our chlorine. And then remember, the OH leaves as water. And so those are our products, right? We get the chlorine where the alcohol used to be, and we get the water as our byproduct. Now, one of the things you have to be really careful about is that one of our intermediates is a carbocation. Right, so if we draw things out on this one, there's a hydrogen that's implied here. And our intermediate that we're going to get is this is going to leave as water. Right, so our hydrogen is going to go onto the OH and make water, so this is going to leave. The problem is this is going to create a secondary carbocation. And so remember, we can do a hydride shift which will lead us to our more stable product, a tertiary carbocation. Right, so the problem with these is they're very prone to rearrangement. Right, so typically what you want to do is see when the alcohol leaves, what kind of carbocation would it get? Is it primary, secondary, or tertiary? And then stop and say, okay, if I move the carbocation one to either direction, can I make it better? Right? Can I make it more substituted, something that's going to make it more stable? And if the answer is yes, you're going to do rearrangement. And the two most common rearrangements are a hydride shift, right? So we move a hydrogen, so that's what we did in this case, or we do a methyl shift. And if you have the possibility of both, typically you'll do a hydride shift first. All right, and then at this point, now your bromine that came from the HBr can add in, and we'll get our product. All right, so let's draw that. And so I think this one's a little tricky because one of the most common wrong answers is just to put the bromine in place of the OH. But we always have to watch out for that rearrangement. The last wrinkle on this reaction is it's not stereospecific. So if we're looking at this OH, it's already on a tertiary. So this is already a tertiary carbon. So when this leaves, we're already going to have a tertiary carbocation. So we're in good shape. So let's just draw the product. And the bromine went in the same position the OH started in because it was already a tertiary carbocation. So there was no driving force to rearrange because we had gone from tertiary to secondary, and the same tertiary to secondary down here. So it didn't help us. But the problem is we had one specific enantiomer in our starting material. When we get our product, we actually get both. We get one where we retain the stereochemistry, and we get one with inversion. And that's really typical of any time you have a reaction that has a carbocation intermediate, you typically don't have controlled stereochemistry. So you won't necessarily get inversion of stereochemistry or retention, you get a racemic mixture. And that's the case here, that will make both enantiomers. So what we get is a racemic mixture. So be really careful. Any reaction that creates a carbocation, which is the case here, you tend to get a mixture of products. So when you do these reactions with HCl, HBr, HI, the two things you want to look for is rearrangement and loss of stereochemistry.